Alright, so chapter 12 is a bit different from its predecessors or from chapters which are preceding it. Uh, in the preceding chapters, you could very well see that we were actually dealing with communication techniques, analog or digital, for various communication channels. While this chapter as the name also indicates, is actually an introduction to a whole new angle of communication, which is noted by the name of information theory. Now, we all know that there are actually three fundamental parts. One is the information source, and we have the communication channel and the destination. So, engineer does not know or does not control what is the information source, nor the communication channel, and also the destination. But what we have a transmitter and a receiver. So transmitter actually connects the source with the communication channel, and the receiver on the other hand will get the information from the communication channel and reconnect it to the destination. So these two systems are completely designed by the communication engineer and are in his control. So another goal design is that we know that we have channel impairments, and we just seen the last chapter that we have band limited LTI channels. So we have ISI, and we have also time varying channels, and they also cause changing. They also call ISI as well as other fading effects. So, design of the transmitter and receiver is that signal must be resistant to the changes brought by the channel of the channel impairments during the transmission. So, as we saw in the last chapter, that because of band limitation, we were getting distortion and inter-symbol interference. Uh, then again, for example, in wireless communication, when many mobiles are communicating over the same channels, you have also problem of interference. So in the previous chapters, we were discussing communication and signal design techniques, and first few chapters were for analog signals, and the rest of the chapters were for digital. But none of these chapters explored the fundamental limits of communication. We even define optimal receivers for digital communication from chapter 8 and 9, chapter 8 and 10 that were studied by us. But again, there was no discussion of overall optimality of the communication system. So this is a fundamental viewpoint which will be studied in this chapter, and here we will basically see what are the fundamental limits of the representation of information, of the transmission of information, how much we can send the data in a communication, and so on. But again, we will have only one lecture, so we won't be able to cover the whole of this chapter. We will be just covering the initial part of this chapter. So the fundamental questions, for example, what is the highest rate at which information can be reliably transmitted, and what is the lowest rate at which information can be compressed and still it can be retrieved, what is the optimality. In all these questions, they belong to a branch of communication theory, and that is called information theory, which we are trying to understand. So main contribution was by Shannon, and these contributions would be in two domains, classified in two domains. One would be what are the fundamental limits, and for that you have to have a mathematical model and some mathematical technique for measuring the information. In this Second question is of source coding. So what is the minimum rate at which the source can be compressed and then it can be recovered from the compressed version? So this is the Shannon's source coding theorem. Then we have the transmission of information over noisy channels, and what is the maximum rate at which they can be transmitted, and this is called the noisy channel coding theorem. So we won't be able to cover the second category, but we will be able to cover the first category, and that is the representation of the information and the fundamental question of source coding. Now, first of all, modeling of information sources. So we have seen that information could be in any form: audio, video, speech, music. It could be in any type, and then we have to transfer this through a communication channel. So you can see the information could be it could be binary, it could be audio, it could be video, it could be analog, it could be digital, and so we require a mathematical model to represent these information sources. So Nyquist, Shannon, Hartley, they were pioneers in defining measures of quantitative measures for this information. And so we will see the modeling of sources define a measure of information, and then we will see how can we make this information more compact for easier transmission. So the process of representing information state of source with a small number of bits, this will be called data compression. So information, we all know, it refers to some new knowledge, and it could be learned from any of the your senses: hearing, seeing, touching, and all that. So information produces outputs that are interest to the receiver, and we do not know them in advance, and the role of our engineers is to receive them correctly at the destination. Information, again, we have seen it is a time varying unpredictable function. So if it was predictable, there was no need to transmit. This we have also discussed in the first chapters. So it is a random process. And then in the communication channel, you have noise, and you might have stochastic dependence between the input and the output of the channel, and you have actually stochastic dependence between the input and the output of the channel, and the communication designer creates a system that transmits the output information source, which is a random process, to a destination, which is a random medium, and ensure that it is delivered with the lowest distortion. So they are a random process, and their properties would be bandwidth, range of amplitude variations, power contents, and statistical properties. For example, PDF, stationarity, and PSD, power spectral density. For example, if you have speed signals from 3400 Hertz, so PSD will also occupy this band, and its PSD is shown. For video, you have a larger bandwidth. For TV transmission, it is basically from 0 to 6.5 megahertz, and you can see in this figure. So this is a PSD of a speech signal. So in speech or in video, we can see one thing, that they are band limited, hence they could be sampled at Nyquist rate or higher, or a sampling rate higher than the Nyquist rate, as you have seen in chapter 7. So we will be focusing our attention to discrete time random processes, where we can see that the actual information signal was band limited, so we have sampled it, and then we are representing that sampled information. The mathematical model for this time. Yes. Bismillah, sorry for the interruption. So क्या कहते हैं, so we are saying that it makes sense to model our source of the discrete time random process, because we have seen that all that the signals are band limited, they could be sampled, and then they could be represented by uh, alphabet discrete numbers. And so we define our random variables over an alphabet, and that can be discrete or continuous, but we will be focusing more on discrete part. So about a discrete time running process will depend on the nature of the information sources. So you could see, for example, that let us say we have seen in chapter 7 also that once you sample, you have to, the signals can again take any values. So you have discrete time but continuous magnitude values, but you can also discretize your magnitude values. So so you have a discrete time random, or you can see that the amplitudes and time, they are both, because they both become discrete. So we will have fixed random variables or fixed values, fixed alphabetical values that the signal would be taken once it is passed through that process of encoding and all that that we studied in the last chapter, in chapter 7. So we will be studying a discrete time memoryless source in which you can see that all the data, they are generated independently, they are not dependent on the previous data, and the data are IIDs, they are independent and identical, and they take a value in the discrete set. So you can see here the values are there. So you could decide, for example, we decided in chapter 7 in one example that there will be only 8 different values or 4 different values. So those values, they will be coming out of the information source. So for example, let us say these are the alphabets that can come out of the source after all the process of discretization, and each of these alphabets, they exist with these probabilities. All right, let us define their probabilities. And so a discrete memoryless source will be given by the alphabet and their probabilities. For example, if I have a discrete source which has 2 alphabets, 0 and 1, and the probability of 1 is equal to 1 minus the probability of 0. So this is an example of a discrete memoryless source. P is 0.5, so both 0 and 1 occur with 0.5 probability. This will become BSS, or binary symmetric source. Now, how to measure the information? So we have just seen that the information is now discrete, it is memoryless source, and the outputs are coming. So we would see in this example actually more information is actually conveyed by the alphabet or by the source which is least probable. Let us try to understand this. So for example, you can see that let us say that we represent a source. We have a source that represents weather conditions and air pollution in a city during July in the northern hemisphere. Now you can see that A represents different combinations of weather conditions and pollutions. So for example, it could be hot and polluted, hot and lightly polluted, cold and highly polluted, cold and mildly polluted, but this is very cold and lightly polluted. So you can see here, this is very cold and this is lightly polluted. So it is more specific in terms of temperature, because no temperature was very or lightly, and then it is lightly polluted. So we know that this will be occurring the least amount of time, because it is a very tough constraint. Both these conditions have to be satisfied for it to occur. So it will have least probable, but it will convey the most information. So AN reveals the most information. So this means that the rational measure of information for an output should be a decreasing function of the probability of that output. And if we have some change, it should not change in probability, not should change the information deliverance by a large amount. So many times we can also divide our information into two sets. For example, here we saw it was temperature and pollution. and they could represent independent set of information, and they might not be related to one another. So the conditions is that the information content will depend on the probability, it will not depend on the value, and then it has to be a continuous function, then it has to be decreasing function of its argument, and if they are independent then it should be a sum. So this a function that satisfies all these properties is the famous minus log x. You could choose any base, but normally we choose to the base 2, for digitization and all that, because we have 0 1 bits to represent, that is minus log of change the base of any by this method log. For example, for log of 10, so log of 10 x divided by log of 10 2, you will get log of 2. So, and then all right, this is the information, but this information will be occurring depending on their frequency of appearance. So the overall information will be written as minus log of x or minus log of pi times pi and then sum over that. So in this way, this is the Mayer, the information content of your information source, and this is called the famous entropy of the source, is denoted by h of x. So h of x is defined as follows. So if it is 0, this will be 0. So h of x, you can very well see it is not a random number, it just calculates and it gives us a number. You can see pp and 1 minus p, 1 minus p, let us say are the probabilities of 0s and 1. So this will be the entropy, and the entropy figure. In this figure, that if you have 0 probability or maximum probability, in that case information is 0, but once you have 0.5, which you have the least probability, which means that both the events are equally probable, you have the highest set of information. So as you can see here, entropy of the binary source is 0 when either p is 0 or p is 1, because in both these cases you are dead sure that this is a probability of 0 or 1. So there is no probabilistic part, there is no random part, it is all deterministic. Okay, and hence it's all predictable. Once it is predictable, then there is no information, because information is the unpredictable part, the new knowledge that you do not know. Once it is predictable, then the information becomes 0. So, but we saw that entropy is maximized when the two sources are equally probable and each the probability of half. So, output is least predictable. This is half will be the case when the output will be least predictable. You won't know it is 0 or 1 because both are occurring with the same probability. In that case, entropy is maximized, and this will support the intuitive development of entropy as a measure of the information content of a source, or a measure of its uncertainty. So you can see this example, these were the sources and these were the probabilities. So we just took their probabilities and took their log part, but this is minus log. So 1 over 2 will become 2, and you just calculate them. This will become actually 15 over 8 bits per sample. So one sample entropy gives us information of the amount of bits that are required to represent one sample. Alright, so he says that, let us say that this source bandwidth was 400 Hertz. It is sampled at Nyquist rate. This means Nyquist rate will be double the bandwidth, so it will be actually 8,000 samples per second. Okay, so one sample requires 15 over 8, so 8,000 samples will require 8,000 15 over 8 bits, or in 1 second you will have 15 over 8 into 8,000 the bits per second. Similarly, here you can see, let us say if we have an alphabet of size n and all of them are equally probable, so in that case this will be 1 over n, 1 over n, and you can do the calculations. This will become log of n, n times n cancels, and you will get log of n. So you have the maximum probability once all the alphabets are of equal probability. Hence entropy will vary between 0 and log of n. joint and conditional entropies. Now joint entropy is given as follows. So you have two random variables. So instead of having probability of a single, you will use the probability of the joint, and you can extend this for n random variables. So h of x, where x is a vector which consists of n random variables, its entropy will be given as follows, where this is the joint probability density of all these random variables. Then we have the conditional random variable. So I would be teaching from the book, but I will be also going back to the lecture notes. So whenever we find that we are missing some part, or especially with respect to the mathematical option, so we will be shifting to the notes. So I think you can also see the notes. So it is a brief description. In book there is a detailed description. So but some steps in book are always missing, so we will be shifting between the book and the notes. All right. Everyone is understanding? I hope everyone is understanding. All right. So now we have conditional entropy. Conditional entropy is called the entropy corresponding to a value of a known random variable. So given the random variable can be defined by noting that if y is equal to y, then the PM of the random variable x will be pxy. This is the main thing. So in that case, entropy, given that the random variable y is equal to y, will be px given y, px given y. Same thing as you saw px, px, or pxy, pxy. So it will be px given y, px given y. Okay. So yes, so this is px given y, and if we want to find px given x, then we will sum this over y, and this will be the conditional entropy. This will be defined next. So this will be px given y, where we will be actually summing not only over x, but we are also summing over y. So you will sum over all the y's, so you will get the conditional entropy. And you can also now define this in terms of multiple random variables. So x of n, given all these, will be probability of this thing. All right, probability of joint of x and x, as you saw xy, probability of joint xy, and then probability of x given all these things. Give x given all these random variables, where you are summing over all the random variables. So you can also was explained. This will be the probability of joint entropy of multiple random variables, and would be x given y, and then this would be x given all values or the total random variable. So in that case, this will be the random entropy for a given one value of random variable, then multiplied by that random variable and summed over all the values of y. So this will give me x given y, right? So if you will put the value from here in this equation, so you can see solution of py into this thing, and you can take it outside and you can combine this as xy. This comes out to be px given y into py. This becomes from the base rule pxy. So pxy log of px given y, as we saw in the book, that formula is given here in the notes. Again, this formula was not shown in the so I think from here we can go to the book. This was, we studied in chapter 5. This rule was actually also used for the base rule. This we have already seen x given y is equal to py given x given y, and this could also be vice versa. Pxy could be px, py given x. You can use both of them, and then you combine them and you get the base rule. So here you have want to prove this thing, that hxy is equal to this thing, and we just start from the basic definition. Xy is xy, and we know xy can be opened up as in chapter 5, py px given y, and then you can uh, open this up, the log of this plus, and this because this minus pxy into log of pxy, so they are both now separated. And if you sum this over x, because there's no x here, so this will become 1. Probability of summation over all of x will definitely give you 1. Joint integral, you are integrating over, in other words you can say joint integral, you are integrating over one variable, so you will get this other random variable, which is other properties of random variable. Joint will become single, and this will become py over integral or summation over y, so log of py. This becomes the formula of hy. Here you have the same thing, but this is actually x given y, so become hx given y. So a very good thing is that the joint entropy of x and y is actually equal to the entropy of x y, okay, plus entropy of x given y. So we already know y, so we now have the information content of y. Then whatever the information content of y given, and then remaining x content information, that will actually give me the joint information content of x and y. On this theorem, I need to repeat. So the information content of y plus information content of y of x after y is known. So yes, so if you want to know the information, either you can reveal x, y, or you first reveal y and then reveal the remaining amount of information in x, and then this can be written in terms of a chain rule, that h of x is equal to h of x1 plus h of x given h of x1, then we have h of x2 given x1, then you will have h of x3 given x1 x2, similarly h of xn given x1 to xn minus 1. So here you can see this x consisted of x1 to xn, so you can write information in h of x as this. If these random variables are independent, so x2 is not dependent on x1 and xn is not dependent on its previous values, you can just write h of x as summation of the entropies of the individual random variables. So entropies of the n random variables is equal to sum of the individual entropies of the individual random variables, provided they are independent with respect to one another. So entropy when n tends to infinity. So what is the entropy of this? And this is the they discuss another formula for entropy rate, which is as follows. So you can see there are two different formulas. One is x of n given all the previous random variables as n tends to infinity, and they are actually similar, but its proof is not in the course. You can just see it. Now let's try to find entropies, various entropies, conditional, joint, and all that. So you have three. You have a joint distribution, 0, 1, 1, 1, 0, 0. So you can see 1, 0 is not there, and all these probabilities add to 1. So this means probability of 1, 0, x being 1 and y being 0, that will be equal to 0. So what will be hxy? Hxy will be these probabilities times log of these probabilities, log of inverse of their probabilities, and add them up and you will get the entropy. So joint entropy comes out to be 3 over 2. Remember, all these logs are log to the base power 2. Then he wants to find h of x. So h of x we know is we need to find the probability of px1. We need to find the probability of px0. All right. So probability of px1 is only this thing, because 1 0 is already 0. So it is only p1 y1 this is p1, and you know y p1 y0 is 0, so this will be only p1 y1, and that will be equal to half. Probability of x1 is equal to half, so probability of x0 will also be equal to half. Similarly, we find the probability of y. So y will again be, because y is equal to 2 times y is equal to 1, so you will add these two probabilities, you will get 3 over 4. So y of 0 comes out to 1. The probability of x1, x0, y1, y0, you can find hx. And then you can also find the conditional probabilities, because you know the joint is equal to this into this, so you can find y or x by subtracting. Similarly, you can find h of x given y, and this will come out to be like this, again from the same formula, but written differently, y given x, x given y, and so hence you can find all the then we have another thing which is called the mutual information. So mutual information is information that is the joint information of the two random variables. So if we have a random variable x, entropy is h of x, but this set, which is entropy of x minus the entropy of x given y, actually has reduced the amount of entropy of h of x, or reduced its information by removing the uncertainty about x with the knowledge that y random variable was known. So this is called the amount of information provided by random variable y about random variable x, and this is called mutual information. Is h of x minus h of x y. It can also be written h of y minus h of y given x. Again, many times it misses the steps, so whenever it misses the mathematics, so we will be going to the notes, but many things are also missing in the notes. In that case, you will be going to the so mutual information is this. We know h of x is this thing. H of x given y, we have seen already. This is given as follows. So here I can take this common, I can take it outside. So this will also be common with this of this, because integrating with py here, this is px, will actually make it 1, so you can also put it here like this. Log of this, then you apply the famous base rule. This becomes x given y is pxy the pxy over p of x. Alright, so this we have already seen. So this comes out to be like this. So this comes out to be the formula of which the book was stating. This one, this has been driven. Alright. So he has shown this figure. We will be setting this figure also, but just to get also do this example. Again, you have two random variables and joint distributions, and you have 0 0 1 0 and 0 1. So you don't have 1 1. All right. You can very well see that. And in this case, you can see px0. It will be a combination of this and this. This will become 2 over 3. P of y0 will be 2 over 3. Okay. And so what will be h of x? H of x will be px0 py0. So px0 log of px0 plus px is equal to 1 log of px is equal to 1. Right. So I have written here px is equal to 1, px1, px0, px0, and you can put the values. Here I have done this deliberately, all the steps. So what I do, log of 3, and this was, this was actually log of 2, 3 was minus, we'll make it inverse, 3 over 2. So log of 1.5, but I use my calculator, so I use, log of to the base 10. If you have scientific, you can use 2. So these were the values, log of 10 of 3, and this was log of 10 of 2. So, by dividing log 10 of x with log 10 of 2, you will get log of x to the base 2. So I get those values, and then I add them, and hence I copy of x, and this will be the same entropy of y. So we have find this thing. So we also need to find hxy. All right. So hxy is very easy because you have 3 random variables, 3 different alphabets, 0, 0, 1, 0, and the fourth one is 0. So 1 over 3 into log of 3 plus 1 over 3 into log of 3. So they will all just add up to log of 3. All right. As we have seen log of n previously, this comes to 1.585. So x given y will be equal to 1.58 minus 0.9. All right. And so mutual information will be h of x minus h of x given y, that has already been found, and hence the mutual information has been driven. And this you can also see that mutual information is 0 whether you say x, y, and yx. So these proof formula, they will give you the same thing. You can also see proof. You can also see from this previous example. And then you can just open up this h of y. This is h of y given x was equal to h of x y minus h of x. So you put the value, then you get this result. So we have a figure here, 12.4, which is also shown in the more properly represented in the book. So you can see here, this was h of x. This total circle was h of x. It was representing the information source, the entropy of the random variable x. Now this total circle was representing the entropy of y. Okay. So hx given y is that the information that that is still present in x, but given y is there. So once we know we have all this information, so we have also this information. So only this information here, this in horizontal line, this information which is left, which is given by h of x given y. All right. Similarly, h of y given x, hy was to complete, but once we know x, so we have all this information. So only this information is left, which is actually given by hy given x. So these are the vertical lines. Now this is the mutual information, and you can see this is actually given by h of x minus hx given y, or you can say h of y minus hy given x, and this is equal from this circle different my subtraction, or from this circle you will get the same result. Last thing is the entropy. So entropy is for differential entropy is for continuous sources. So for continuous sources you will define it like this, because it is continuous. You have to have summation, you have to have integral. Rest of it remains the same. For example, if you have uniform random variables, the 0 to a is its probability to its PDF is 1 over a, all right, 1 over a minus 0, log of 1 over a, and this becomes log of a, and you can check this. So a little bit different from the entropy for discrete sources, but still they are defined in this manner. So this is for entropy for Gaussian random variable. So you can very easily, this will be again log, but we will take ln, so that ln compares with e. Then we can convert ln log natural of e to log natural of 2 at the last step. So this multiplied by f of x, this total multiplied by f of x, this means that log this multiplied by f of x, and this multiplied by f of x. So here you can see that this is totally constant, this comes out, and fx integral, this will be 1, so you will just have log natural minus, will make it in the numerator. Here again this log natural will e, this will cancel, and this power will come here, minus minus will cancel, will become x square over 2 sigma square. So 2 sigma square is just a constant, but x square into fx, this is sigma square over 2 sigma square will actually come out of this integral. And then you can very well see, you can write this as in terms of log natural e uh, to the power this, because you know like log natural e is 0, the log L and log natural e with this is the power. You can also represent it like this, and then you can uh, combine these two terms. So this will become log, this under root will become half 2 pi, and this will become actually this will become sigma square, sigma, so this will cancel, this will just become half. I can write this as log e to the half, and this half comes here, half log of e. Alright, so this half also comes here, these both half added, this becomes half of log of 2 pi sigma square. This 2 has already been taken out, but there is a log of e, so 2 pi sigma square e. This is log natural of e. You can convert this to, you know, log natural of 2 by dividing this by log natural of e 2. So this will get log natural of 2. One distribution, this will be conditional, this will be mutual information there, and similarly. Then we have the last topic of this chapter. This is called the source coding theorem. So this is a fundamental theorem. Yes, fundamental theorem. It establishes the rate at which information source can be compressed without causing a large error probability. So a very good explanation is given. This question is not in the notes. Just for your explanation and your and to increase your inquiry knowledge, or your knowledge related to you know the inherent nature of human beings to know the unknown, assume that we have a DMS and we are observing outputs of length n, n set of data variables are being observed, and n is very large. So A1 is the probability of alphabet 1, A2 is the probability of alphabet 2, A1 is A1 is the letter A1, alphabet A1, its probability is, let us say, is P1, A2 is probability is P2. So in n sequence, as n tends to infinity, its probability of occurrence will be NP1. Very simple. Okay? Similarly, for A2 will be NP2, and so on and so forth. So we are trying to go to a typical sequence, the sequences that will mostly occur as n tends to infinity. So the probability of my sequence as n tends to infinity will be actually, you can see the product of the probabilities of the individual alphabets, and the individual alphabets, you know, their probability is pi, but they will be occurring npi times, so it will be pi times n and I, and product with all of the other terms. All right. Now I can represent this pi npi as 2 to the power npi log pi, because you know npi will go here, so become log pi npi, and this, you know, is log of 2, so 2 to cancel, this will again become pi npi. So these two terms are same, so no problem. And then, you know, this product, this goes into the power, this becomes summation, the summation of log pi log pi. You can take n outside, this becomes h of x, this becomes 2 minus h of x. So probability will become 2 minus of these sequences. So these typical sequences, when n is very large, are equal probable, and their probabilities are 2 minus hx. So and they are equiprobable, and the probability of this means the total number of sequence will be inverse of this, it will be 2n h of x, right? N h of x was for, you know, if we are observing the length of n, if we are observing the length of 1, so the length of one symbol in terms of bits will be actually just h of x. Yes, remember outputs is 2n hx. These are the typical sequences, so you can see we need nhx plus to represent, but for one, for the it could be this, but you know, typical sequences will be 2 NHS, which will be most probable. So you need n bits. So for one source, you will require hx bits. So you can see why this hx is so important. This h of x gives us the amount of bits that are required for one sample once we have these typical sequences. So this gives the shortest or the most compressed rate. We cannot have any compression beyond this rate. Discussion you can see here. So this gives us a famous source coding theorem that let us say we have a source which has entropy H. Then if you are sending that source with this rate R, which is greater than H, no problem, you still have a small error. But if you choose the rate to be less than H, then the error will grow. So how can we achieve an algorithm that can source code the alphabets with the given entropy of the source? Okay. So there are two algorithms, Huffman and this Lempel-Ziff. So in our course, we just will be discussing Huffman source coding, so that we understand this Huffman source coding. All right, this will be understood here. So the main yes. So you will see this is a fixed to variable length coding. So the main idea is that more frequently occurring fixed length sequences, they are mapped to shorter binary sequences, and less frequently occurring sequences, they are mapped to longer binary sequences, so that we can have good compression ratios. So synchronization will be a problem, and we will see how will that get rid of that synchronization problem. So assume that we have these sources, these are the alphabets, and there are these probabilities. So we use 4 different codes for their, for coding them. All right. So let us see. We see the first code, which is like this. We see an advantage that in all of these codes, all the codes in code 1, all of the code words they end with 1. So a decoder will always know that once there is a 1, this means a code is ended and a new code will start. This is called the famous self-synchronizing code. In the second code, you can see all of the codes are starting with 1. So this is also a self-synchronizing code, because the decoder will know once a 1 is there that a new code word has started. But again, you can see that this is not as desired as the first code word, and the reason is that in the second code word we have to wait for the next code word to know whether the first code word has ended, because once the next code word starts with 1, then we will know that the previous code word has ended. So you have to wait for that, but in code 1 you don't have to wait for the next code. So you can see that yes, 1 and 2 are uniquely decodable, but only code 1 is instantaneous. Only code 1 that you can write it instantly. Well, you can decide instantaneously. All right, the code is ended. This is the code. This will be the alphabet. Then we have code 3. Code 1 and 3, they satisfy property that none of them is a prefix of another code word. So they did satisfy the prefix condition. When they satisfy the prefix condition, they both become uniquely decodable and instantaneous. So they are self-synchronizing, but at the same time, they become uniquely decodable, and so you just decide instantaneously, because this is a unique code. This is not in any other. So this will be the code, okay, and hence I decide that this is my output. You are never in a fix that whether this was a code, because every code is different. None is the prefix of the others. You have to decide only one way. Hence, this will be uniquely decodable. So 1 and 3 are uniquely decodable. So what is the code length of 1 and 3? So in code 1, we have these probabilities, and in code 3 we also have these probabilities. But code 1 has these lengths 1, 2, 3, 4, 5, and while that has 1, 2, 3, 4 length. You can see here one has 1 2 3 4 5, and code 3 is 1 2 3 4 4. So that is, you can see the average length for code 3 will be less, with 30 over 16. Okay, that is why code 3 is the best. And with code 4, you can see it has a majority disadvantage because one of the code is prefix of the other code. In that case, you won't have unique decodable. Code is not uniquely decodable because 110 can be decoded as A5 because 110 is A5, so it could be A5. But at the same time, 11 is A4. You can see here, A4 is 11, and then you have A2, which is 01. So you can say this will be A4 and this will be A2, and then 10 is A3. So you can decode it both ways, A5, A5, A4, A2, A3. So this is not desired, and this has to be avoided in practice. So code 3 is the best code, and code 3 is called the Huffman code. So we try to, in Huffman code, we try to choose the code words so that again most probability have shorter code words, and then we want the length to be approximately of log 1 over pi, so that you can achieve the entropy of the source. So they are optimal. They are unique because they are instantaneous, and they have the minimum average length among all codes. And they also satisfy the prefix condition and all that. So this is the coding algorithm, and you can see how you have to operate this algorithm. First of all, you will put all the code words in order of their probabilities. Then you will merge the least two probable outputs. All right, and in this way you will continue. If let us say only two steps, two alphabets with their probabilities they are remaining, then you will just put 0 and 1 and you will finish. If still more than 2 are, then you will again go to 2 and you will again merge the least probable, and this way this will continue. This table is also shown, and you can copy from there also. Yes. So once you have you have combined the alphabet's probabilities and you have assigned 0 1, then what you will do, any code which is an alphabet which actually comes from the merger, you will append a 0 and a 1 to obtain the code from the preceding outputs, and you will repeat step 5 so that no output will be the output in the current step. So all the outputs are coded, and then you can stop. Let us try to see this example. This example is also given in the notes. So first of all, you have these alphabets. All right, these their representations were not known at all. Right. So this we have to find through our Huffman coding, how to represent them in zeros and ones. So, but we know their probabilities, so we arrange them in order of their probabilities. So first of all, you combine the lowest two probabilities like this. 1 over 16, 1 over 16, this becomes 2 over 16 or 1 over 8. Then 1 over 8 and 1 over 8 are combined, and this will come out to be 2 over 8 or 1 over 4. Then 1 over 4 and 1 over 4 will combine, this will become 2 over 4, this will become 1 over half. After that, you have half and half, and you have only 2 remaining, so you will just give 0 and 1 arbitrarily to 1 to 0. 1 will be given 0, other will be 1 1. So the code will be 0 for this. This will be 1 0. This will be 1 1 0. This will be 1 1 1 0, and this will be 1 1 1 1. Now you can find the average length of the code. So average length of the code will be the length 0 1 2 3 4 4 times the probabilities, and you sum them up, and you can find the he has not find that, but we have done that in the notes here. So once you do that, it comes out to be 30 by 16. Same entropy, this was 30 by 16, and the average length is also 30 by 16. All right. So you can see that both of them are equal. So this means it is an optimal algorithm, and it attains optimality. It attains the entropy of the source where it's coding. Again, we have this code 1/3, and you can find the the both 0, 1, because all of them equal. You can combine any two 0, 1. This becomes 2/3, and then 0 and 1, and you have 0, 1, 0, 1, 1. So lengths are there. It comes to 1.667, and if you find its entropy, it comes to 1. So entropy is less. Okay. So this could happen that it doesn't obtain optimality. So this is the difference or the gap between h of x and q of x. So again, this example here we are taking the alphabets are taking two random variables at a time, and the value of each individual was 1/3. So you can see the probability for each will be 1/9, or 1/3 into 1/3. So I've taken all the combinations. 3 are 9 different combinations of 1, 1, 1, 2, 1, 3. Then we have 2, 2, 2, 1, 2, 2, 2, and 2, 3, and so on and so on. All these combinations are there. Each of those combinations will have a probability of 1/9. Because they are 9. So I apply the Huffman coding. So all of them are equal probable. I can combine any two. So I have combined for these two, 2/9. These two are also combined 2/9. They combine to give me 4/9. Here I also combine this 2 and all in the first step, because all of are equally probable. 2/9, 2/9. And once 2/9 is to be combined, this becomes 1/3 or 3/9. This becomes 1/3. It goes with this, becomes 5/9. So 1, 2 remains 0, 1. And then you can put the alphabet. So this will be 1, 0, 0. 1, 0, 1, and so on and so forth. The book, there is one mistake I just wanted to point out. So here, this will be 0, 1, 0. Yes, this is correct. 0. This will be 1, 0, 0. He has written 0, 1. This is wrong. You have to follow 1, 0, 0. Follow on the right hand side, and you can put the so. So here, the average code the length comes out to be 3.22, or you can see 1.611. You divide this by 2, so because you are taking 2, so you get 1.611. Now, if you compare 1.611 with this case, when we're taking one symbol there, it was 1667. And we were getting 1.585. Now we are getting average length to be 1.61. So we are approaching more closer to h of x. This means as you increase the length of the code, you are approaching more and more towards the optimal value of the entropy. Okay. And this ends the course. If you have any questions, you can ask. So the course for this chapter will be source coding up till this Huffman coding. Okay. If you have any questions, you can ask. And Salman sir, are you present? All right. Any questions? So for first you will have to give the midterm, and then final course outline will also be shared once the midterm result is announced. But what will be the final? It will be after chapter 6, including the digital portion as well as this information theory part. So I will end the lecture. Thank you very much. As you all have no questions, so I will end the recording first of all.